Imagine a liquid so bizarre that it defies gravity, climbs walls, and flows endlessly without losing energy. A substance so strange that it challenges our understanding of physics. This isn't science fiction, it's a superfluid, and it could be one of the most fascinating phenomena in space. Deep in the vastness of the cosmos, where temperatures plunge close to absolute zero, matter behaves in ways that seem impossible. Under these extreme conditions, atoms stop behaving like individual particles and begin acting as a single, unified entity. This transformation gives birth to a superfluid, a state of matter that moves with zero viscosity, meaning it can flow forever without resistance. On Earth, scientists have observed superfluidity in helium-4 and helium-3 when cooled to temperatures near absolute zero. These elements undergo a quantum phase transition, allowing them to move without friction. But space offers a unique environment where gravity is nearly non-existent and temperatures can reach levels far lower than anything achievable in laboratories. This makes space the perfect testing ground for superfluid behavior on a grand scale. One of the most fascinating aspects of superfluids is their ability to defy gravity. In microgravity environments, they form unusual structures, moving in ways that break our expectations. Unlike normal liquids that settle at the bottom of a container, a superfluid spreads out evenly, as if unaware of the concept of weight. If placed inside a spacecraft, it wouldn't just stay in a cup. It would coat the entire surface of its container, forming a thin, uniform layer. If disturbed, it wouldn't splash or ripple like water. Instead, it would form eerie, wave-like motions that never fade away. One of the most famous experiments demonstrating superfluidity in space took place aboard the International Space Station. Scientists studied how superfluid helium behaves in microgravity, allowing them to observe quantum mechanical effects that are difficult to detect on Earth. The results provided insights into fundamental physics, revealing how particles interact on the smallest scales. This research has furthered our understanding of quantum mechanics and the behavior of matter under extreme conditions. But superfluids aren't just an interesting anomaly. They could be key to future space exploration. In the quest to understand dark matter, some scientists have proposed that it may share similarities with superfluid behavior. If dark matter acts like a cosmic superfluid, it could explain why galaxies rotate the way they do, solving one of the biggest mysteries in astrophysics. If confirmed, this theory could reshape our understanding of the structure of the universe and how unseen forces shape its evolution. Superfluidity may also revolutionize spacecraft propulsion. Since superfluids experience no internal friction, they could be used in ultra-efficient cooling systems, keeping sensitive instruments at stable temperatures. This technology could be a game-changer for long-duration space missions, where managing heat is a constant challenge. Furthermore, the lack of resistance could allow superfluids to be used in next-generation propulsion systems, increasing efficiency and reducing energy loss. Scientists are already exploring ways to harness these properties for advanced fuel transfer and fluid management systems aboard space missions. Beyond propulsion and cooling, the behavior of superfluids could also have applications in quantum computing. Superfluid systems operate under the rules of quantum mechanics, where particles behave as waves and exist in multiple states at once. This makes them a perfect candidate for developing ultra-fast and energy-efficient quantum processors. By observing how superfluid particles interact, researchers may unlock new pathways for computation, encryption, and data processing in space-based systems. The implications go even further. Superfluid-like states could play a role in neutron stars, some of the densest objects in the universe. These stellar remnants have cores under immense pressure, where nuclear forces push matter into exotic states. Some theories suggest that inside these extreme environments, neutrons themselves may form a superfluid, allowing energy to move through the star in ways we can barely comprehend. This could help explain strange pulsations observed in neutron stars, where sudden shifts in their rotational speed defy conventional physics. Some researchers even speculate that certain types of black hole behavior may be influenced by superfluid principles. The way matter collapses and interacts in the accretion disks surrounding black holes might exhibit similar properties to quantum superfluidity, potentially leading to new insights into the physics of singularities. If true, this could provide a link between general relativity and quantum mechanics, two of the most fundamental but conflicting theories in modern physics. Ordinarily, when light enters a medium, like water or glass, it slows down. This effect is responsible for phenomena like refraction, where a straw in a glass of water appears bent. But when light interacts with a superfluid, something entirely different happens. Instead of simply slowing down, light waves can become entangled with the quantum properties of the superfluid itself. This leads to effects that seem almost paradoxical, light bending in ways never seen before, behaving as if it were flowing through a cosmic river with no resistance. But could light itself become a superfluid? Scientists have conducted experiments where photons, the tiny particles that make up light, are made to interact in ways that mimic superfluidity. In these experiments, light stops behaving like individual particles and starts acting like a smooth, flowing liquid. When this happens, something astonishing occurs. Light waves move through obstacles with almost no scattering, as if they were gliding effortlessly through space. Now, imagine a universe where vast regions of space behave like a superfluid. Some theories suggest that the very fabric of the cosmos might possess superfluid-like properties on a cosmic scale. If this is true, then light traveling through space might not simply move in straight lines, but instead flow like ripples in an invisible ocean, subtly guided by the quantum nature of reality itself. One of the most mind-bending implications of this idea is that it could change the way we think about black holes, gravity, and even the nature of time. If space behaves like a superfluid, then light may interact with it in ways we can't yet comprehend, bending, warping, and flowing in ways that defy our current understanding of physics. So, can light pass through a superfluid? The answer is far more complex than a simple yes or no. Light doesn't just pass through, it dances with the superfluid, intertwining with its quantum nature in a way that challenges our very perception of reality. And if light itself can become a superfluid, then we may be on the edge of discovering new physics that could reshape our understanding of the universe itself. In the end, superfluidity isn't just a strange quirk of ultra-cold matter. It's a glimpse into the hidden symphony of the cosmos, a world where light and matter merge into something beyond our imagination. And if we can unlock the secrets of superfluid light, who knows what doors it may open? Perhaps, just perhaps, the universe itself is whispering its answers in the ripples of the quantum sea.